The second part, and probably the more stressed part of this unit, this is the thing that I would like for you to focus the most on in this lesson today, is how to actually interpret a graph, interpret values from a graph, how to evaluate using a graph. So we're given a graph, and then you're asked a bunch of questions: domain, range, finding values, given values, and moving from that. So this is the main idea from today's lesson, is that I want you to be able to make evaluations from graphs. Now these evaluations won't always be so easy. So number 2 and number 3 on these notes are pretty easy evaluations. They won't always be so nice, but we're going to practice it with nicer numbers and then make our way through this lesson or through this unit to harder numbers. Okay. So the first thing that I want you to focus on is the domain. And I do believe, because this is important, that there's a dot here where this curve ends. And so I'll go ahead and add that in. So the domain is the set of all x values. Which means that if we're looking at the x-axis, we're looking at how far along the x-axis has this graph taken up. And it's taken up all the way from -5 up here to +7. And it does end here. Since there are dots, that means that it ends there. Since it's a closed dot, it means it includes that value. Notice on the back, we'll have an open dot, and we'll talk about what that means. But a closed dot means that we include that value in our domain. So that means that we are all the way from -5 to +7. And let's try and remember how we write this notation. Remember that we do D for domain equals, and since it's the set of all x values, we use curly brackets to denote a set. And it's all x values, and x is true here because we're talking about a graph, such that x lives between -5 and 7. We're going to put less than or equal to because we do include those values in the domain. Okay, let's look at our range. The range is the set of all y values. So now we have to kind of shift gears and look at how tall and how short are we in this graph and which y values have we used. It's hard to tell sometimes because it's easy for us to kind of understand this idea of reading from left to right, but reading from left to right or up to down is hard with these functions because you notice that like we relapse and cover certain things. So you might want to say like, oh, like -3 and -4 because you're looking at the endpoints. But that's not really what we're looking at. We're looking at this idea of like walls coming in. Maybe you can think of like old school Star Wars movie of the like trash compactor coming in with Luke and Leia in the trash. But it's the idea of these walls coming in and being stopped by your graph. And so where do they get stopped? Well, the lowest place that they get stopped is right here on this point, and that point is -5, versus up here where they get stopped is at -1. So that is what my range is I'm all the way from -5 to 1. And notice that even with just this curve right here, we've covered all of the values in between. So the range is the set of all y values such that y lives between -5 and -1. Okay. Moving on, what is g of 5? G of 5 means that, hey, x equals 5, right? We've replaced x here with 5, and then it's saying, hey, what is y when x equals 5? So we go to the x value of 5, and then we go down until we hit our graph. And this is where we've hit our graph at an x value of 5. So you can think of it as a line this way, and then you go and look over to the side here and say, well, what y value happens at that point? And the y value that happens is -3. So you can say that g of 5 is equal to -3. 3. But the y value is equal to negative 3 when the x value is equal to 5. If you want, you can write this as a point. So the final point would be 5, negative 3. So notice that there's just a shift in notation because we're learning a new notation, but you're still finding the same values, finding a y value given an x value. It's just a different way of writing it. Okay, g of negative 2, I would like for you to do that on your own. So g of negative 2, we're going to go to an x value of negative 2, and we're going to go down until we hit our graph. Once we've hit our graph, we then shoot over to the y-axis and say, what y value is that? And that's a y value of also negative 2, negative 1, negative 2. So g of negative 2 is equal to negative 2. The point would be negative 2, negative 2. It doesn't ask us to write a point, but I just want you to see that is a conclusion that you can make there as well. Okay, the next two problems are slightly different, but just barely. It's saying, hey, g of x is equal to negative 2. And it's saying, what is x? Or where is g of x equal to negative 2? So given that y is equal to negative 2, what is your x value? We've already answered it up above that we know that g of negative 2 gives us negative 2, but we have to be really, really careful with these types of problems. Because remember that a function is, for every input, you have exactly one output. So for every input that we've had, g of 5 and g of negative 2, there's always been exactly one output. But that rule is not the same flipped. You can have multiple inputs that give you the same output. Because I could write negative 2 here, but that's not the only answer. If I go to my y-axis and find negative 2, notice I have 2 points that are along the x value of negative 2. And their x value, or sorry, the y value of negative 2. And those points are at 0 and then negative 2. So you would say x equals 0 and negative 2. Okay, go ahead and do F on your own. F is a little bit easier than E, which is nice because we're going to go to negative 1 on our y-axis and think about anything that hits negative 1 all the way across, and there's only 1 point, and that is at the x value of negative 1. Okay. Backside, last problem, you're going to be doing most of this on your own. We are going to talk for a second about domain and range together, and then the rest of them you'll do on your own. Okay, so this has different end values or end behaviors from our previous graph. Our previous graph just had points at the end of this graph, which means that it's a very distinct, this is where it starts and this is where it ends. Whereas here we have one end that has an arrow, which implies that it goes on forever and ever and ever in this behavior. And now on this other end, we have an end behavior of an open dot. And these open dots here indicate that we go all the way up to that number, but we don't actually quite hit it. So whereas in the previous page we said less than or equal to, in these cases we would say strictly less than. Okay, so the function's domain. We're looking at the x values that are happening here. So we're looking in this, like what's going on in the x-axis, or the idea of the doors closing in this manner. And hopefully you notice that with this arrow, that means that our x values never really end in this negative direction. They will still continue to go forever and ever and ever in that direction forever, which means that we're starting at negative infinity and then go all the way up to here, which is an x value of 2. So x lives between negative infinity and positive 2. The thing is that we cannot include 2 in that. So we're strictly less than, which we've already talked about. We're also strictly greater than negative infinity. And the main reason is that negative infinity is an idea, it's not a number. So you're going all the way forever and ever and ever towards infinity, but you never actually hit infinity, because the idea of hitting infinity goes against the actual definition of infinity, which is kind of strange and otherworldly, but that is the case, that you can never be equal to negative infinity, because if you were equal to negative infinity, then you wouldn't technically be at the idea of what infinity is. I'm going to finish writing this out in my proper notation, x such that, putting my curly brackets around it, and there you go. Okay, the range. So again, we're talking about the doors closing, opening and closing in this way. Sometimes it's hard to tell. We get distracted by things like this, when actually the lowest our number is going to be, our y values are going to be, is right here, and that's at positive 2. So we know that y is going to live between 2, and since this arrow is going up and up and up and up and up forever, that means that our y values are going towards positive infinity for forever. So it lives between 2 and infinity. We do not include infinity, so we're strictly less than. However, we do include 2 because there is a closed dot at 2 implying, hey, we include it. So we're going to be greater than or equal to 2. I'm going to put my official notation in it, curly brackets, y such that, hey, the range is equal to, and there we go. All right, go ahead and do the rest of these guys on your own. F of 1. F of 1 means that when our x value is equal to 1, what is our y value? So you can draw your lines up this way and then over to the side if that helps you to visualize what's going on here. When x is 1, our y value is 3. So we can say f of 1 equals 3. That would be the point. 1, 3. F of negative 3, I'm going to go over to negative 3, go up to my graph, and then over to my y-axis, and notice that f of negative 3 is also equal to positive 3. F of x equals 2 means that I go to my 2 values on my y-axis and say, hey, where does the graph hit it? And it hits it in only one place, which we're pretty thankful for, and it happens at the negative x value of 2. Only one answer for that. Where does f of x equal 0? So we're looking at a y value of 0. The graph never hits the x-axis, which means it never has a y value of 0. So we would say undefined here. And that's it. So the main things that I want you to take away from our notes today are, can you find domain and range from a graph? Can you evaluate functions looking at the graph? This is what we mean by evaluating functions, finding what is f of 1, what is x when f of x equals 2, those sorts of things. And then can you understand the idea of a parent function, transformations from a parent function, and graphing using a table of values? You do not need to be an expert on parent functions and transformations from parent functions. They're just helpful. They're working smarter. We're making more connections with things that we've learned in the past and seeing where it all kind of comes together and to what purpose, to what end. Great job today, and we'll continue this next time I see you.